So let's continue with filters in the frequency space. And nope. Let's see. Oh, my mouse is on the wrong place. So now it's right. So, and what we have is then we started working with the Fourier transform, and most of you probably have seen the one-dimensional Fourier transform, which is the one that you come across mostly in the calculus classes. The Fourier transform can actually be expanded to any dimension. So it's only that you have to take care of frequencies for each dimension. So the whole equation becomes a bit uglier because you have to add the additional domains. But I'm actually not going to dig so deep in that right now. But in practice, what you have is that you can work with the fast Fourier transform, and that works at least for 2 dimensions. I believe it would probably also, in most packages, also take the 3rd dimension. But that depends on the implementation. And a little bit basics of the Fourier transform. You have some basic signal here. If you have 2 signals, one with a low frequency, one with a higher frequency, if you sum those, it looks something like this. It's a bit hard to understand or see, but if you compute the Fourier transform, you get very nice frequency responses for each of these components. So here, if you add this signal, has the peaks very narrow to the center. So actually the Fourier transform has positive and negative frequencies. So, and these peaks are centered around 0. And here we have the next one, which is high frequency. So it goes further away from the center point. And if we sum them, we can nicely see that all these peaks, they sum up, and you have peaks for each frequency. And you can easily identify that you have to clearly have 2 frequencies. Again, there is a nice video about the Fourier transform in 1 brown, 3 blue that you can also watch if you want a recap. And the interesting thing about the Fourier transform is that convolution can be made much easier. Before, we saw that the convolution, then you have to actually do some kind of repeated sums for each point. And if you do the Fourier transform of a convolution, it's actually the multiplication between the image and the Fourier transform of the kernel itself. So this is a very nice feature of the Fourier transform and can be used in some cases. Alternatively, you can also say that the multiplication in real space turns into a convolution in Fourier space, which is then a bit inconvenient, but sometimes you need to do that too. So first of all, let's create some images to observe this. We have these 2 juggling balls as an image. We have some noise, and when we sum it, this is the image you get. And these are actually not color images, just pseudo colors. Makes it easier to actually see the contrast here. So if you compute the Fourier transform of this, it looks something like this. And typically what you see is that you have along the central line, you have a cross. That is the bias, the background information in the image. And in the middle, you have a large peak, which is the main bias in the image. The noise, however, if you have Gaussian noise, it's homogeneously distributed in the whole Fourier space. So there is nothing, no structures, and that is what we call white noise. So it's homogeneously distributed on all frequencies. If you sum those, now our contrast is not fantastic, so maybe you have to look in your lecture notes later. But what you can see is that in this one, you have a little bit kind of spread, intensity spread out in the quadrants, and that is buried by the noise level because that sums up on top, and the only thing you see is then some parts of this cross. Now, how to produce a filter now in the Fourier space? Before we said, I actually mentioned that we had low pass and high pass. Then I talked about frequencies, also that we have slow variations are low frequencies, fast variations are high frequencies. And now we want to apply a filter to reduce the noise, say low pass filter. And for that, first of all, we have to define the filtering process. And the filtered image is, in principle, the Fourier transform of the image times the Fourier transform of the filter kernel. And then this product, we do the inverse Fourier transform, and then we have our filtered image. And a basic low-pass filter is one with a hard threshold in the frequency domain. And let's see if I can move up. I can't. Okay. Then we have our noisy image, which has also a spectrum. Here I use the logarithm because I want to highlight a little bit more the low amplitude. And our filter window defined like this looks like that. We have zeros outside here in the dark region, and the yellow disk is our pass band. So that is, in principle, all the low frequencies, they are passing through unmodified. So if we multiply these two, then you can see that the filtered image looks like this. And then we do the inverse Fourier transform, and we come back into the filtered image. And you can see that the noise has reduced, but we also have some more blurring, as we can expect also from what we saw before. So this is just a different mathematical framework to do the same thing as I showed in the previous lecture, previous part of the lecture. Another one would be to apply a Gauss filter. And again, the interesting thing with the Gauss function is that the Fourier transform looks exactly, has the same shape more or less. You have to juggle a little bit with the parameters, so the sigma comes in a little bit differently, but in principle, it's the same function once again. So we have a Gauss bell as a filter window, and that gives us a distribution of the filter weights, so we are a little bit more sensitive towards outside here, towards the higher frequencies. And then we have our Gauss filtered image. Here I also provide the code how to do it. And one interesting thing is I'm not only using the Fourier transform, but I'm also using a function called FFT shift. That's a technical detail about the fast Fourier transform, that it reshuffles the quadrant. So the zero frequency, which we expect to be in the middle, is actually up in the corner, and the minus smallest frequency is down in the right lower corner. So the frequencies are opposite to each other. So FFT shift is reshuffling the quadrant so that it looks like this. So that is mostly needed. Either you do it on the image or you do it on your filter kernel. That you have to choose what you want to do. But here I did it on the image. And then when you do the inverse transform, you have to do the shift again to get it back to what the fast Fourier transform wants. So you can also play a little bit more funny thing with the filter kernels. You can do a bandpass characteristic, so you only want to focus on the low frequency parts around the axis in the two directions. And then you essentially start having an orientation sensitive filter. And this example was just to play, and you will see that you have a lot of kind of cross-like patterns in texture in this filtered figure. You get a strong low-pass filtering effect, but the cost is now that you distort your image. But this in mind, you can actually also do very matched filters to what so you can optimize the filter to the signal properties. And one is the Wiener filter, which is a signal optimal filter. The original definition is this one, and it can even be used for deconvolution. So if you have this H here, that would be your convolution kernel from, say, your acquisition system. And ideally, you could use this even to sharpen your images. Deconvolution is, I would say, an unstable problem, so it's tricky to get it right. In the Fourier space, it looks very simple, but don't be fooled, please. It's really a tricky one and unstable because you divide by a function, and then you easily come to singular points, and everything just blows up, and you get nothing useful out. It's a whole different topic, and I'm actually not going to go into it. That would probably be a lecture of its own, at least. But if we reduce it, we can have the power spectrum of our image, and here and here, and then we just add the effect of our white noise, so it's a constant level. And with this function, when the signal is much stronger than the noise, then the filter function turns into 1. If the signal spectrum is much less the sigma, then it goes to 0. So we are sensitive to this noise level. So it's a kind of a thresholding in the filtering. And the effect is, coming back to the balls again, you can see that we have this spread out in the quadrants, and the filter kernel looks something like this. So it actually takes care of more information out in the spectrum as compared to, for example, the strong hard threshold filter kernel or the Gauss filter. Looks a little bit more like the Gauss filter, actually. And then we have the filter image that looks like this. So this is a way to go in some cases, and I will actually come to a conclusion afterwards what kind of filters to use and when. Another interesting thing about the Fourier transform is that you can see orientations, or you can actually identify orientations in the data. So here I have some images in real space, ripple with different orientations. And when you compute your Fourier transform of these ripples, you can see that this one, then you have the two response peaks. They're just opposite of each other in the vertical direction. If I had 30 degrees, these two dots, they are rotated, and 60 degrees even more, and at 90 degrees, they are horizontal. So with that, you can actually start doing some kind of orientation analysis, and also in pattern recognition to some and hidden deep down in the convolution and neural networks, this is actually something that is taken care of and investigated. And there are some filter classes where you have these patches of orientations that you can use for signal output. So, how can that be used? In this case, I designed a matched filter for some structures. We did some experiments, and unfortunately, the normalization wasn't successful because the background was changing shape all the time. So we got these stripes in our background in our background field, and they were quite annoying. So we wanted to get rid of them, and the approach was actually to look first at the Fourier spectrum and identify that, yeah, these stripes here, there should be something a little bit tilted along this line here. So what I did was to create a kernel looking like this, with strong filtering at low frequencies and a little bit less out at higher frequencies. And when I applied that one, I got rid of quite some degree of these stripes, and that was sufficient to produce better reconstructed images in the tomography, because this was just a single projection from a tomography, and we need many in order to do our reconstruction. And before applying the filter, we had this cloudy, inhomogeneous background, and also within the sample, and that was quite annoying for later segmentation tasks. And after applying this filter, we got rid of that cloudiness and had nice images that we could work with. So this is an application of how you can have orientation-sensitive filters to get rid of unwanted structures in your images. And of course, there is a bunch of filters for this. We have for the convolution, median filters. We also have the Fourier transform, and as the Fourier transform works with the complex numbers, it's also good to know that you can actually extract the amplitude, the angle, real and imaginary part of these numbers. Now, I'm stepping up to a different kind. Actually, now it's again going back to noise reduction, but we saw that we got this blurring from the convolution filters and the median filters, which we don't want. So a new approach is to work with scale spaces, which means that you downsample your image to different scales and do some filtering on each scale. And that can be helpful when you have textured noise, for example, because the textured noise, to get rid of it, you need so large convolution kernels. And then you would destroy the information. So the trick here is that you go to different scales to address different sizes of structures that you want to remove. And as you can see here, on first few scales, it's about the same information, but it gets a little bit more harder to see them. On this level, it has reduced quite a lot, and then the last one, well, then we have done too many scales, so that one is not really useful. And the first thing that comes to mind when you talk about scales is the wavelet transform. And that is a transform that, in principle, has this scale idea built in. And the good thing is that you can transform to a different scale, but you also have the way back to the same image again. And what you do in the wavelet transform is you separate the image into a trend part and a detail part. And the trend part is a low pass part, and the detail is a high frequency part. And then in the transform sequence, you always take the trend and apply the transform again. And then you take the trend, apply the transform again. And always you save the detailed part. And that may sound a bit abstract when I explain it like this, but looking at this example, you can see in 1D, we have this base signal where we have a sine wave and a square wave and some added noise. And when we do the first decomposition, so we're downscaling it by a factor 2. And then we have this signal, still a bit noisy, a little bit wiggle on it, but it's getting a bit better. And the detail looks like just pure noise. The only thing that you could possibly see is around these edges, you have a little bit more spikes. And then we can take this one, decompose again into a trend, detail, trend, detail. This almost looks like a sine and a square wave, actually, without any noise. And then the wavelet transform framework allows you to, with the help of this, only this trend part and all the detail parts, to reconstruct the original again. With images, it's of course stepping up one dimension. So here we have the trend for horizontal and vertical. In this corner we have the trend for the vertical and the detail for the horizontal, opposite, and here we only have pure details. And the decomposition goes the same way, but here we now have 3 different detail parts and only one trend. And then we take the trend, decompose into this one, the trend, decompose into that one, and so on. Looking at an example image, This is just a lot of geometric structures. And with this visualization, it's a bit hard to see the large parts, but I actually have done the decomposition at different levels, put everything into one image. And first down here, you can see that actually this one looks at the horizontal parts, this one looks at the vertical parts, and this one, well, barely visible, but it takes the diagonal part. So now let's look into how we can use this for applying a filter. And in principle, what we do, we do this decomposition. Now I only do it in one level. And looking at the detail, seeing all the peaks that stick out from some threshold level, they must be signals. That's the reasoning at least, and must be kept. And that gives us that the thresholded signal looks something like this. And we put those together. We take the trend and this one instead of that one, and then we have some filtered image. And it works in a way. Of course, now this is just a conceptual idea. Also, in this example, I have done this kind of thresholding, and actually I don't know how many times I decomposed it, but I must have done 2-3 levels in the decomposition. But here is the original noisy image. You can see line artifacts, you can see also maybe some ring artifacts, and the denoised one looks like this. Still see some blurring, and an interesting thing is you can maybe even see this ripple. That's an effect, that's a kind of an artifact introduced by the wavelet filter. I honestly didn't put so much energy into doing this example. You can probably, by the choice of the right decomposition base, get better results. Can also do smarter. I mean, I just did a thresholding in the different levels. But still, you can get a pretty good reduction effect here. Then another way to do this scale space is to go towards parameterized scale spaces, and then we actually start solving differential equations on the images. And the first approach, so here are some examples, but I go deeper into those. One is a starting point, taking the heat transport equation, which is this differential equation where we put T, so the temperature, as the image intensity, and K, thermal conductivity, is how strong the filtering is working. And the basic idea is that when you let the temperature distribute, at some point the whole sample or object homogenizes to the same temperature. So it's a smoothing effect that you get from that. But the problem is, as you can see here, it pretty soon smooth out the image completely, so you don't really have anything left. And then we're back to the problem of distortion beyond recognition. So what the people started doing, thinking that, well, maybe we can control the diffusivity or heat conductivity. And that was done through applying a threshold or a function that thresholds based on the gradient in the image. And well, there were different of these control functions, but the basic idea is if the gradient is low, do a lot of diffusion. If the gradient is high, do little to none diffusion. And the full equation then turned into, so the kappa turned into this function. And this function produces from that image this kind of diffusivity map. And you can see that around the edges, it's almost no diffusion, and in the flat areas, there is a lot of diffusion. The problem is only this function here is based on the gradient. And we have already seen also that the gradient is very noise sensitive, as it's very local, looking at the difference between two adjacent pixels, which can be noise burdened. So what was done was actually to apply a Gauss filter. So that's a gradient with a sigma, means that it was applied a Gauss filter to the gradient. And then all of a sudden it turns much better. You have the original here, and you can do quite some nice, let's see if I can run it. Yeah, it runs all the time. Yeah, you see that there is an improvement in the signal to noise ratio in the image. It even takes out this line artifact after a while, and these are the effects that we want to see. This filter was also implemented in 3 dimensions, a topic that I haven't mentioned yet. Until now we look only at 2-dimensional images, but if you have 3-dimensional data, you should actually use the 3-dimensional filtering techniques to avoid structural dependencies between slices. Then there was, that wasn't good enough, so people started looking into regularization techniques, and that came out with filtering, where we had optimizations based on either the absolute norm or the mean squared error norm, and that turned into pretty much better filtering. And the basic idea of these, the diffusion filters, they work first looking at the small details, and then after a while, after some iterations, you get more and more smooth. This one puts everything upside down and identifies the large regions first, and then it goes down into the small details, which gives also a better edge preserving in the filter. And then we got a little bit uglier equation here, a coupled differential equation that needed to be run over the filtering, but the effect is, oh, this is dark. The effect is that you can get really strong filtering, and near the edges here, you still have a very nice defined edge. This filter has the effect that it's producing locally almost like continuous patches if you don't watch out. So it's a tricky one to configure and get the right numbers, but we use it actually quite a lot, this kind of filter. Then time went on, and people started looking at something that's called non-local means. And the idea here is that when you apply a convolution filter, you look only locally on the neighborhood and do averaging in that local neighborhood. With a non-local, the filter idea is that you try to identify patches that have about the same intensity and shape distribution and filter all those together. And that gives you much stronger statistical support to get a better denoising effect. And what is happening is that you apply the filter. It has many parts, but in principle what it does is, one part is to compute this comparison function that gives you a weight, and then you apply that to the image. I have produced a demonstration notebook, but I noticed that there was some transfer error, so I have to upload the right one afterwards. But there you can see how this non-local effect is working. And the problem with that filter is actually it does pretty good denoising effect. I mean, you can see here the noise is essentially gone. The rings, they're not gone because they are very strong structures in this case. If it was in 3D, I think the rings would also disappear. So what we get is a very good smoothing effect from this filter. And the strong lines, they are preserved, and also strong edges. So it can be very sensitive to fine details, which is what we actually want. We don't want the small features to disappear, as I showed in this little disk example with a Gauss filter. We don't want them to disappear mostly. The rings, we would like to, but in this case, they are not gone. And then you can actually also get a little bit of patchiness in the filtering. that could be an effect. You can even see in the comparison here that there is a little bit of squared patches in that. So there is a little bit of a complication in the performance because the complexity is big O n squared, because every pixel has to be compared with every other pixel. And that's quite time consuming, particularly if you go for three-dimensional images. Myself, I did a naive implementation, and I realized to filter 1K cubed image would take astronomical times. Even though I tried to throw in some threading, it wasn't a good idea. What people do instead is they reduce it into small patches, which can be more efficiently filtered. And then you kind of instead come into an n squared, which is much quicker. And then you could also implement it on a graphic card, and people can do it nowadays in reasonable time. Another thing, that was the notebook, which I have to upload in the right way. There was a problem with the large file storage on GitHub, so that one got lost. I need to fix. Another one which was developed with the same kind of thinking as the non-local means, but takes it one step further, is the BM3D filter. BM stands for block matching, and 3D is that actually a bit confusing, because the 3D looks like it's a three-dimensional image, but it's actually for two-dimensional images. And what it does, it extracts patches with this, again, with similar features, put them together into a three-dimensional image, which is then filtered. And there are quite some algorithms here. You can actually download also in Python. There is a BM3D package, so you can try it yourself. And the idea is that it has a reference patch, and then it tries to find all the patches that have the similar feature. So also here along this line, and that gives you a very nice filtering effect, because it's collaboratively filtering all these patches together. And another nice thing, when I talked about the inverse scale space filter, it was tricky. I didn't say that it had 4 parameters that you have to juggle against each other. In this case, it only has 1 parameter, and that's the noise variance in the image, which makes it very attractive. You can also use the noise power spectrum, which would make it even more efficient, because in that case, it actually in the background somewhere has a Wiener filter, which would be very happy about seeing the noise power spectrum. Some examples. Here we have the non-local means, total variation 1, which would be the inverse scale space, and the BM4D. So here it was actually done on a volume, so that's why it's called BM4D. And what you can see is that there is less smearing. So in this one, you have some smearing, you have some edge unsharpness. With the total variation, you have a lot of unsharpness, and then with the BM4D, the unsharpness is getting less. This was actually taken a little bit out of its context, because I think we even did the filtering on the projections before reconstructing, and that's why you got all these extra things. But this was the original, so it was pretty noisy, and still you can reconstruct very nicely all the transitions between different edges. So today, I would say, without going into machine learning, the BM3D 4D filter is probably the strongest one that produces the least patchiness and the sharpest edges in your images. But it takes time to compute. Here comes a little bit about the 3D images, also for BM3D. You require, of course, quite a lot of memory to compute this, and that can be a bit a trouble too, because you need a large computer. If you have 1K images, you easily explode up to 32, 64 gigabytes, sometimes even more. of RAM just to process these images. So there you have to maybe also go into block processing to make it feasible. The denoising can actually, under certain given circumstances, go even further than BM3D. And that is where the machine learning is coming in. And you can do this denoising with the help of machine learning. And here are some examples. You have the non-local means, you have the BM3D. You can already see here that the non-local means, it has a very much smearing effect on the images. The BM3D does a pretty good job. And here are two more examples. Actually, this one I'm not so convinced about. It looks like she had a bad day and when she did the makeup. But that one really looks amazing. And I believe you have to look at those on your screen afterwards. But these are really very detailed, requires a lot of training of the network to get there. So it's not that you can just pull it off the shelf to get nice denoising with the machine learning approaches. So now I've been talking about a lot of denoisers and to improve your images, and the question is which one to take. Well, you may say take the best, but the question is actually what is best for your images and your processing task. And when you want to choose it, you have first of all to say, do you have a 2D or 3D image? You have to have some idea about the general image composition. Is it a lot of flat regions? Do you have gradients? Do you have lots of fluctuations in the image? Also, which level of detail you want to have preserved and how noisy your images are. And practical thing, which filters do you have access to? Which ones can you just pull down in your tools as logging as a toolbox? Do you have to implement them even? I mean, these previous ones, the machine learning ones, they are not off the shelf. You have to really implement them. You have to do a lot of training and so on. Maybe it's the right choice for you, but you have to be aware that there is a lot of work to do it. Which is also, do you have the hardware to use the filter? You can easily blow up your memory if you don't watch out. And of course, how much time you have. One is, how much time do you have to implement a filter? Because you need to maybe to implement it. And the other thing is, how much time do you have to use it? Sometimes, if you only have a single image, you can spend days. If you get the perfect filtered image, you can spend days on it. It's nothing. But if you want to process 1,000, then you have to start thinking, yeah, 2 days times 1,000, well, that was my PhD. So, so you have to make a choice, a smart choice of how much time you have versus what kind of filter you use. So the question is, you have to compare and see a little bit what performance you can get and what you need. Oh, I'm running away in time. Yeah, okay. Talking a lot today. Do you mind if I step over the break? It's okay? Yeah. So the other thing you can do with filters is actually looking at orientations and analyzing these. Here I have 3 examples. I have some ball packing, a slice. I have a picture of hair, and I have a peacock feather. And we see in these images we have local orientations and we want to measure them. And the first approach would actually be to look at the gradients. We have already seen that. If you look at the gradient, this one, you can see the typical bright and dark flip. In the hair, it's a little bit difficult. It's more complicated. Also in the peacock feather, you can see this dark, bright ripple. Depending on which gradient you use, you can see the vertical structures, you can see the horizontal structures. So in principle, the gradient is the right way, but the question is how robust we can make them. So if we start looking at the local orientation, so we just look at the angle between the two gradients, and then you see here, well, there is an indication that we have different orientations, but the problem is also on different sides of the edge, you have a positive and negative orientation, which is a bit confusing when you want to do the analysis. Also, these look a bit confusing, I would say. We saw also that the Fourier transform can tell us about orientation. If you do it on the local image, it's very hard to tell anything about the orientations. You may get a little bit information, for example, in the feather. You can see that there are two dots here, maybe, very weakly. So that indicates we have some clear structure with very nice frequency, but it's still hard to detect it. Another more robust approach is to compute the structure tensor, which is actually all the gradients combined. And again, this one, we come into the problem that the gradients are very noise sensitive. So what we do is we also here apply a Gauss filter to smooth it a bit. And this would be a function to compute the structure tensor. And the fun thing with that one is, let's look at the different components first. Here we can see that the diagonal ones, they look at the vertical and horizontal structures. And the diagonal ones, actually, they are essentially the same. They look at the diagonal structures. And with this tensor, we can compute the eigenvalues, and this is where it starts to get more interesting, because with that, we can look at, for example, the coherency, where we look at the different, or this normalization of the lambda max and min, which turns out into that equation. But the interesting thing is here, the coherency factor is that in regions where C is equal to 0, that means the two lambdas are about the same. That is a flat region without any structure in it. If it goes towards 1, then we start to have a very distinct orientation in it. And of course, as these values vary, are not discrete, then we have a little bit local orientation is between these axes. So looking at the ball packing, that's the easiest one to look at. We can see that the coherency, local coherency, is very strong around the edges, and that is actually where we have our orientation information. And then from that, we can also compute the local orientation angle with the help of these values. And then we can see this one. Now you can see that the problem that we had with the gradient is gone. And you can see that we have red here, which is the positive angle. Here too, it's the same. And then we have blue, which is the negative angle. So this starts making more sense than we had before. And it's not so noise sensitive because we have included also the Gauss filter in this process. And looking into these textured images, then we can see that in that one, the local coherency is very strong everywhere because we have lines in the whole image. And then we can see also the angles. They have some clear structures. We have something here. So here we have a flip between just a little bit in that direction and a little bit in that direction. So that's where we can see here now the blue and red shift. If we look at the histogram of that one, we can also see that the global orientation in this image is apparently around 0 degrees. So there is about equally many in each direction. And looking at the peacock feather, it's, oh, that one I should hide. Okay. Then we can see there is a shift towards the 45-degree orientation. So we can actually already from this information tell where we have the orientations in our images. And yeah. if we look at, so this is more detailed, we can see here the general direction in this one is apparently around 0, and in this one is around 45 degrees. Now, we can use this also to look at, compare locally. So we take patches, and we can see that this patch apparently has something around here. That patch has moved a little bit. That patch is clearly in the 45-degree direction, and that we can use to quantify our local orientations in the image. And we need to then do patch-wise comparisons, and then from that we can get these local orientation angle images, which may be a bit difficult to comprehend. But if we instead show them as a vector field, we pretty nicely see which trend these orientations have. So, last section is verification. How good is the filter I have produced? And now I'm mainly going towards the denoising. And in principle, my former boss here was always talking, can you trust this data massage? How much do you modify the data? And in principle, as I said, every filter does some kind of modification of the image. The question is only if you invent new features or if you actually enhance and are true to whatever there is in the image. And the first step is actually in the verification of your or the validity. The first step is actually just look at the images. Does it make sense? If it doesn't make sense, go back and do something else. In that, it's very good to work with also difference images. And if you want to go into the big task, then you can also work with degraded phantom images or actually using database images where you have some ground truth and do some, well, what I call a smoke test. So let's looking at the difference images. We have a noisy image. And the ideal filter would actually just lift out the noise from the image. If your filter is a bit too strong, like if you have a too wide Gauss filter, you will see it like a halo around the features in the difference image. That gives you an indication that, oh, something is not right. Then you can have intensity scaling, which is also a common mistake. If you don't put the scaling on your convolution kernel in the right way, then you will have a change in amplitude, and that's not what you want. And the last one, the geometric shift. If your filter kernel doesn't have the center in the right place, you will shift your image in some direction when you apply it. So this helps you actually also with in the visual inspection, but that's a qualitative first look. And if we want to do a more quantitative approach, then we have to do some kind of performance testing. And the smoke test is actually something I got from the electronics. Back when I did my own circuits for a long time ago, the test was how well does it work? Yeah, pull on some power and see where it smokes, which is the weak point. Well, you can do essentially the same on this. In principle, what you do is creating a phantom image with relevant features. Then you add noise. And then you apply your processing chain on it and measure the difference between the processed and the phantom. And then you can tell how well your method is working. And this you repeat several times because noise is statistical. So you want to have more statistics to get a good test, tell how well it is. And then afterwards you can plot these ranges with different parameter scans and different signal to noise ratio and see what the result is. So what you can do is you can apply known models. In this case, the Shep-Logan phantom is very often used for medical imaging applications, tomography reconstruction. This was a structure that I created for a root segmentation algorithm. So I had some kind of branched structures, and I want to see how continuous I could keep them during the processing. Then we also have the data for that we saw last week, the MNIST digit database, and that can also has label data, which can be helpful in this task. And for the quantitative part, we want to have some kind of metrics, and the typical ones used are the mean squared error, which is a very simple one. Not always a good one, but it's a first go-to because it's easy to compute. Then we have a structure similarity index, which includes local averages, local correlations, standard deviations, and some stability parameters. And then you can compute that as a number that tells how good images are. But in principle, what you need is always a ground truth and a processed image in these cases. And for that, here is a test run example where I had different structure sizes, and I tried to detect them as good as possible. And those I played again also with the signal-to-noise ratio and contrast, combined with the sizes, and that gave me then a test result that I had different noise levels and how well it responded at different signal-to-noise ratio. Also for different sizes of the structures. And yeah, that was the outcome that I used to see how well my algorithm was actually working. So we are at the end. I have here now talked about many filters. Actually, these are not all I have mentioned, but this is an overview of the different filters and how they can perform. I have the original without noise here. Then we have with different signal-to-noise levels. You can see this one is really ugly, and how well these perform. Looking at the detail, you can see that the Gauss filter, or the box filter actually, introduces a lot of blurring, which is not really ideal. But the other filters, they are pretty good. The median filter, as you can see here, cuts out the corners because they are not sufficiently dominant in the median compilation. And yeah, then you can see down here in the really noisy case, the ISS filter is still producing a very smooth image, which is not too damaged. So when you want to choose your filter, you have to start in the practice. Start with a simple one. It's quick to compute, doesn't cost you anything. See what it gives you. And then you can do that iteratively, check what is the effect of this filter on my use case, check if you have shifts in the bias and boundaries. You can also see how much signal-to-noise ratio you improved it, and if that's good enough, be happy, just use it. Otherwise, you can always go to more and more advanced filters, and there should be, of course, a motivation to use the filters that take 2 days to compute. And otherwise, it's important also to know that filtering changes the noise variance, so it improves the signal-to-noise ratio, usually. It also changes the spatial resolution, and could be changing a bias in the image. With this change of spatial resolution, it also changes the detectability of features. So be sure that if you want to do some quantification, does the change of the filter actually improve the image, or does it distort it to something that biases your conclusions? And yeah, we have all these filters, so the best thing is not asking what is the best filter, but actually what is the measurement target, what we want to measure, what spatial scale is relevant, and how much bias is acceptable, and if computational time is limiting. So in the end, in principle, we have seen all these filters can save your images, but it's always better to do a good measurement in the beginning so you don't have noise. So yeah, and also we can use the filters to provide quantitative information about orientations. And that was the end. So thank you for today.